Next, we're going to finally see the exact definition of the definite integral, which is, next to the derivative, one of the top two most important concepts in all of calculus. So the definite integral is written as follows. So we would write it as the integral from a to b of f of x dx. This is read as the integral from a to b of f of x with respect to x. We previously saw, just with a tentative definition, that this corresponds to the area under the graph of f of x between a and b. So if we compute the area here, so let's call that a1, and then we compute the area down here, we'll call this one a2. So the area a2 is below the x-axis, so that one's counted as a negative area for the purposes of the integral. So the integral from a to b of f of x dx would equal a1 minus a2. So the area beneath the x-axis is counted as a negative, and the area above the x-axis is counted as a positive. Now, we previously saw how to approximate the area under a curve. So we approximate the area under the curve by taking small little slices. So delta x is b minus a over n. So we divide the x-axis into n subintervals. And then we have these notches. X sub I is equal to a plus I times delta x. So here's a, here's b. So this is x0 and xn, and then our notches are placed in between x1, x2, x3. So these are the values of where the intervals start and stop. And then we said our Riemann sum was a sum I equals 1 to n of f of xi star times delta x. And so xi star is some point on the ith subinterval, so it's some point between xi minus 1 and xi. So it's any point on that subinterval. And the idea is that f of x sub I star is the height of our ith rectangle, and delta x is the width. So when we multiply these two together, we get a rectangle like this, and we look at its area, and we add up the areas of all n rectangles. So as delta x becomes smaller, in other words, as we use more and more subintervals, as n gets larger and larger, the width becomes smaller, and the function varies less and less over that subinterval, right? So if I get my magnifying glass and look at a tiny little sliver, the function's height gets very, very, close to being constant, because there's just such a tiny space for it to vary. So as you use more and more subintervals, the exact point of where you approximate the function doesn't matter when you use many subintervals. Now, a few things to note for this whole concept of the Riemann sum is that for each value of n, you have to redo all of this. So this isn't just normally it's not a straightforward function of n. Everything here in this Riemann sum depends on n, the number of subintervals. Delta x changes, right? Delta x depends on n. Your x sub I changes. For example, suppose I have, here's a and here's b. Let's say I have 1, 2, 3 subintervals. This would be x sub 0, x1, x2, and x3. Now if I divide it into 5, I'd be dividing it at different places. I'm not just adding more notches. The notches are moving around, because if I divide this interval into 3, or if I divide it into 5, or if I divide it into 7, the notches are not lining up. So the x1 here is not going to be one of the notches if I use 5 subintervals. So everything about this thing changes. But it does depend on n. The one thing, so for a fixed function f of x and for fixed a and b, this Riemann sum basically depends solely on n. You give me a number n, and I can tell you what the Riemann sum is for that many subintervals, right? So if you say, let's fix our function f of x, let's fix a, let's fix b, you say, okay, n is equal to 10, go. I can sit down and compute what the Riemann sum is for 10 subintervals, assuming we agree on what type of Riemann sum, if it's a left hand, right hand, maybe a different type of Riemann sum. But if we say left hand Riemann sum, all left hand Riemann sums will, that will uniquely tell you an output. If I use the right hand Riemann sum, it will be different. But as n gets larger, the left hand and the right hand Riemann sum get closer and closer together, as we saw previously. And they get closer to any other Riemann sum we can dream of, right? Because as we get the smaller and smaller subintervals, really, really small, the function can barely change in such a small delta x. So all the Riemann sums ultimately approach the same value. So that said, we can finally define the definite integral. So the definite integral, so this is the correct definition of f of x. So we had a tentative definition that just gave us a conceptual understanding. This is the formal definition. So the definite integral of f of x from a to b is defined as, so it's the integral from a to b of f of x dx, and it's equal to the limit as n goes to infinity of the sum I equals 1 to n f of x of I star delta x, right? So basically, here's your Riemann sum with n subintervals. And as I mentioned before, that Riemann sum, however you choose to compute your Riemann sum, the value that you get for your approximation will depend on n, assuming we agree on what particular type of Riemann sum. Then you can have a function of n. So if it's a left-hand Riemann sum, okay, I tell you n is equal to 10. The left-hand Riemann sum with 10 subintervals is whatever. If I use 100 subintervals, I get whatever. So basically, this is a sequence of numbers, right? So for each value n, I get a different output. And then if I use n is equal to 1,000, I get a certain output. If I go back and I have to recalculate everything, I have to recalculate my x of i's, my delta x, redo the whole thing, n is equal to 10,000, n is equal to 100,000, n is equal to a million, a billion, a trillion, a Google, 10 Google, and so forth. The outputs will approach a specific value. They will approach the exact area. So in the limit, as n goes to infinity of the Riemann sum, it gives you what we call the definite integral of f of x. Now, I noted earlier that there's different ways to compute a left-hand Riemann sum, right-hand, any other Riemann sum you can define. There's ones called midpoint and trapezoid rule, and there's other ones still. So it's a more advanced result that you might get in an upper level analysis class, but all of those Riemann sums will approach the same value in the limit as n goes to infinity. So we're not so concerned about which Riemann sum we're using for these purposes. But just the understanding is, in the limit as n goes to infinity of this, you get something that we call the definite integral. And notice that f of x sub I star can be positive or negative. So if f of x is positive, this area counts as a positive because the output here is positive and delta x is still positive. If f of x is negative, this counts as a negative. So that is kind of, you can see why you get positive area up here and a negative area down here, because the values of f of x are positive and negative. So that's the definition of the definite integral. That's the formal definition. Only for a few very basic examples, can we compute this easily. And the good news is we won't have to. We have some powerful technology where we can integrate relatively complex functions easily. So that's the fundamental theorem of calculus, which we'll talk about soon enough. But for now, that is the definition of the definite integral. So if you want to know what the definite integral means, it's the limit of a sequence of Riemann sums. So computing this is a process. You usually don't get a straight up function of n here, like you normally see when you take a limit. Some cases you can, and you can work that out, and we'll see a few examples. But most of the time, you just have to think about this as process. Okay, I can compute a Riemann sum for any number n, so let me just go down and, hey, let's try it with n is equal to 100 and see what the output is. Let's try it with n is equal to 1,000, n is equal to 10,000, and so forth. And hey, these Riemann sums are approaching this value, so that's an approximation of the limit.